So I wanted to make this video to maybe go into a little bit more detail on the Euler-Lagrange equation because whilst the last video constructed the equation, it didn't really infer exactly why it was useful and the general most common use case of it, which is a minimization condition for functionals. And so I wanted to bring up a commonly used example to describe just how it's so useful and just how powerful it is. So we're going to again work with the thrown ball example, but this time we're going to use a parabolic trajectory, again, in absence of any dissipative forces. So we throw a ball from the floor at time equals 1, and it travels parabolically through the air until time equals 2, or t2. But let's perturb this system a little bit with a perturbation function. We'll call it eta. So we'll define a new function y star of t is equal to the original function t plus a small amount epsilon, which is a small little variable, times eta of t. I think that's the right name, right? Eta. Someone correct me if I'm wrong. I'm not so great with the Greek alphabet. So eta can be anything you want it to be, but it has to satisfy that eta at t1 is 0 and eta at t2 is also 0. So we can draw eta on here. It could be some, like that, whatever, right? It could be anything. And that's going to, adjust the path here a little bit up and down, whatever. It could be anything. So then we'll consider a quantity called the action, right? Which is normally denoted as s. And that's going to be the integral from t1 to t2 of the Lagrangian we described in the last video, which is, a sum of the kinetic and potential energies. It is, the action is really what it says on the tin, right? It's the integral of energy with respect to time in this capacity. So that's going to be a function of y and y dot, and also t, but I'm not going to write it because it's kind of inferred, right? So we want to find a condition that minimizes the action, right? And we're going to minimize it with respect to epsilon. So if we take the derivative of the action with respect to epsilon at epsilon equals 0, we expect the action to be a minimum there. When epsilon is equal to 0, we have the path just y, which is a perfect parabolic arc, which is what we observe a ball to travel in. So we expect that to be the minima of action, because why would nature expend more energy than it needs? So we can move this integral sign dE inside the integral, so t1 to t2 of dl, which we're going to use L of the starred y path, so it will be y star, y dot star. So I'll just write that whole thing as L star, right? Epsilon dt, right? And then we can use the multivariable chain rule to express this in terms of y and y dot, or y star and y dot star. So that will be the integral from t1 to t2 of dl star over dy star over d epsilon plus dl star dy dot star d epsilon dt. So of course that's a little bit long, isn't it? But it makes sense, right? It's just the multivariable chain rule. So what is d y star d epsilon? Well, it's just nu, right? Of course, because that goes away, and then epsilon goes away, so it's just, oh, not nu, sorry, eta, my bad. My Greek is playing up again. Really, it's a hard language, I'm awful at languages in general. And of course, we expect this to be stationary, so it's 0, right? So I'll write 0 here. And so this just becomes t1 to t2, dl star dy star, oops, that's my earphones, eta, plus, and then this, the y dot, if we just differentiate this, everything just becomes dotted, and it stays the same, so the eta will just be dotted, so dl star dy dot star eta dot dt, right? So that makes sense so far. I hope you can see everything, right? Yeah, but the thing is, we don't really want an eta dot here. We want everything in terms of eta, so we can cancel it out, right? So how can I kind of redraw this in terms of just eta alone? Well, if I take the derivative with respect to time of dl dy dot, all starred, times eta, well, we'll using the product rule, the we get the time derivative of dl star dy dot star times the dot of eta. Oh, sorry, not times the dot of eta. What am I talking about? Just times eta. Plus dl star dy dot star times the dot, right? And so that's that, right? They're identical there. So if we just subtract this term from both sides, then that's going to be equal to this. We can just sub it in, right? So 0 equals the integral from t1 to t2 of dl star dy star eta plus the time derivative of this whole thing, so dl star dy dot star eta even minus the time derivative of dl star dy dot star times eta outside the derivative dt. So again, pretty long, right? But here we've stated that eta has to be 0 at t1 and t2. So this integral here, the integral will cancel out with that ddt, leaving just this between t1 and t2. That's just going to go straight to 0, right? Because of that condition. So we're just going to be left with this. So I'll write that out. T1 to T2 dl star dy star eta minus d dt of dl star dy dot star times eta dt equals 0. And so this is looking a lot more like the Euler-Lagrange equation, right? And we can divide through by eta to, because it has it on both terms. And we're left with this equation, which is obviously the Euler-Lagrange equation. But what does it mean? I mean, what does it really mean? Well, we expect the action, like I said, to be minimal, to be the least when epsilon is equal to 0. We expect the change in action to be minimal when epsilon is equal to 0, because of course that's the path we observe in real life. And again, why would nature expend more energy than it needs to? So a direct consequence of that simple premise is the Euler-Lagrange equation. You can think of it like a derivative test, a stationary point test for functions, but in this case it's a stationary point test for functionals, like I described in the last video. And this works for any functional of the form. We usually use a generalized coordinate, so instead of y or x we use q, because that could mean y, x, it could mean anything, right? So for any functional that is a functional of q dot and whatever the derivative is with respect to, in this case time, this function will minimize, this expression will minimize that functional, which is very useful for finding, again, trajectories. So in this case, that would give you the parabolic trajectory. It's also very useful for finding things like the backrystochrone, which actually I can show you that quickly. Because the backrystochrone, I mean, that's the prime example of the Euler-Lagrange equation, right? We have a value time, t, capital T, which between 2 points A and B is just the integral of dt, right? But what is dt? Well, dt using speed equals distance over time is just the arc length of some curve of the form y equals f of x divided by the speed, which is presumably a function of x and y. And of course, ds is the square root of dx squared plus dy squared, or whatever coordinate system it is. And so when we sub that in, we can take out a factor of dx. So we'd get t equals between, oh, my pen's really running out. I hope you can see it. Whatever, I'll still describe it. So that will be 1 plus dy dx squared over, again, some function v of x and y dx, right? So notice this is a functional, right? Because it has a dy dx, a derivative with respect to x, that has a y in there, and it also has an x in there, right? So we could employ the Euler-Lagrange equation where this expression inside the integral is the functional, and find a path that minimizes the time. which is the macrystochrone. So you can see how useful it is there. It's very, very, very powerful because there are a whole class of functionals which are applicable in physics. So yeah, I hope that's a useful derivation, and yeah.